This is Aerodynamics podcast number 45, and today we're talking about contraction design in wind tunnels. The contraction is a very important part in wind tunnels. So you have the fan. This is pretty much in all wind tunnels. You have the fan, then you have the flow conditioning section. So you usually have a honeycomb, then some meshes, and then you have the contraction. The contraction links the first half of the wind tunnel to the test section. And the contraction is what it says it is. It contracts from a very big cross-sectional area to a very small cross-sectional area. And the reason why we have contractions, there are two main reasons. The first is that by reducing the cross-sectional area, we increase the velocity of the flow because you have the same amount of flow that needs to go through. The density is the same. The area drops, so the velocity needs to increase just through continuity. So that means we can get a much higher velocity than what the fan is outputting without having to run our fan faster. The second reason why contractions are very important is because the contraction makes the flow a much higher quality. So what it does is it squeezes all the flow and it makes it go in the same direction even more. So the honeycomb helps straighten the flow, but the contraction does this even more. So it's a very important part, and there are contraction ratios that most people follow. Usually around a wind tunnel is usually between 5 and 15, depending on how good you want the flow to be. With that comes a pressure drop, which is a negative effect, and you can also have separation and etc. So that's why the contraction design is very important, and that's what we're talking about today. To do that, we're going to be looking at a paper called a computational simulation study of fluid mechanics of low-speed wind tunnel contractions. And this is an open access paper. You can find it in the link below. And what they looked at were 4 different contraction wall shapes. So you have the slope so obviously with the contraction, you go from high cross-sectional area to a low cross-sectional area. And with that, you have to have a slope because you need to reduce that area. And you can have very different slopes. You can have straight, you can have a second order, third order, fifth order polynomial, etc. And they look at 4 different types. They also look at the cross-sectional shape of the contraction. So you can not only have a circular cross-sectional shape, you can have a square, rectangular, or octagonal. The circular one is obviously a very desirable one from the point of view that the fan is usually circular. So if you have a circular fan, it's easy to mesh a circular cross-section with the fan. The problem is that the test section is usually not circular, it's usually square or rectangular. So now you need to somehow mold this circular cross-section to this square cross-section, and then the corners become a very big problem where you have all these dead pockets of air because now you have to like sort of shove air into those corners to make the flow uniform. That's very difficult. What's more, trying to curve a circular cross-section through a contraction, so the walls have to curve and move, it's very difficult to manufacture. Alternatively, you can have a square or rectangular cross-section for the contraction. That makes it much easier to mesh with the test section, and also with the corners, you can alleviate a lot of the problems that you have with the circular cross-section, but then meshing that with the fan becomes a problem. So then you can get something called an octagonal one, where it's an octagonal shape, and that is sort of kind of the best of both worlds. It's not perfect still, but it's very good in terms of how it performs. And I look into these different cross-sectional areas as well. So let's move on with the paper and talk about what they did. So interestingly, they say, according to an ISO standard and an ASTM standard, so 2 different standards in the world, they request that the flow uniformity and turbulence density in a wind tunnel should be less than 1%. Now, the turbulence density of less than 1%, that's not necessarily the case depending on what your application is. So for the wind tunnel application, a wind engineering application, a turbulence density of 1% is quite low. Usually you want to get maybe 5%, maybe even higher. That's because it's supposed to replicate the outside conditions. And wind is not usually very well behaved. Usually it's like 1%, 5%, 10% turbulence density, not 1% or 0.1%. So below 1% is usually for more aerodynamic wind tunnels for cars or for airplanes and stuff like that. But a lot of wind tunnels like that. Like usually, like I would say, 95% of wind tunnels out there, they want to have a turbulence density less than 1%. There's only like 5% who want to have it higher to mimic wind engineering applications. They say that in the paper as well, that the contraction is the most critical component of a wind tunnel to influence the flow quality within the test section, since it is located just upstream of the test section. That is potentially true. I mean, I would argue that the fan is the most important part, because without the fan, you don't have anything. Now they're saying with the flow quality, but also with the fan, that does affect the flow quality. So agree to disagree. They say that the contraction is more effective in suppressing velocity variations and turbulence densities in the longitudinal direction than in the lateral direction. So that's really interesting. It means that the turbulence density, which is in the u velocity, so the free stream velocity, that's suppressed better with a contraction than the v and w velocity, so the lateral velocities. That's something to keep in mind. Then they talk about the contraction ratios, so how much surface area you want, how much cross-sectional area you want to reduce by. They say that Meta and Bradshaw, which are two well-known researchers in aerodynamics, have suggested that a contraction ratio between 6 and 9 are usually sufficient. And that is true. Most wind tunnels will be around 6 to 9. You can get lower, 5, you can get higher. For example, one wind tunnel, they say the NIST has a contraction ratio of around 15. And that's very high. What that means is you get a very good quality flow. You have very high speeds. The problem with that is that you can potentially have worse, like some separation, but also a higher pressure drop, which means that the fan has to work harder to shove all the air through. So these are some downsides. And also it means you need to have a much bigger room to put your wind tunnel in. If your test section, you want a cross-sectional area of 1 square meter, that means you need to have a cross-sectional area for the contraction of 15 times that, 15 square meters. That's a much bigger structure, which means you need to have a much bigger room. And that also means it needs to be longer, so you can contract in a longer space, so you don't have problems with flow separation and with even greater pressure drops. So these are trade-offs. They say that although a very long contraction can be used to avoid flow separation, it usually results in a thicker boundary layer, and that's true. So the longer that the flow can travel across the surface, the thicker the boundary layer will be. That's just normal. Now, you can get rid of the boundary layer. There are boundary layer control devices. For example, you can have a scoop at the front of your test section. What this means is at the bottom, you have this raised surface. The test section is raised from the contraction exit. So the boundary layer actually goes into the scoop, and then the rest of the flow, the clean flow, hits the test section. So that's how you can get rid of boundary layer. And another way is boundary layer suction. So at the front of the test section, you have a suction zone where it sucks out all the flow on the surface, and that's the boundary layer. And then you get rid of the boundary layer that way. And you can have other things like, for example, the tangential blowers, and I'm not going to go into those because they're very specific and they are difficult to get right. It's usually a boundary layer scoop and suction, which are quite common. They say that as we mentioned earlier, the curve of the contraction can be anything. It can be straight, it can be second order polynomial, so quadratic, or it can be a third order or quartic or whatever. They say that here, a researcher called Hernandez and another researcher called Su, they both recommended a third order polynomial curve because that will give the best exit flow conditions. But then Bell and Meta, they came along and they said, we'll see your third order and we'll raise your fifth order. And they say that it's better for avoiding flow separation, giving minimum boundary layer thicknesses, and providing better flow uniformity as compared to the third order and even a seventh order. So don't try to beat us on that. We'll see if that's true or not. So is third order better than fifth order, or fifth order better than third order? This is one of the debates that's brewing in this paper. It's quite juicy. So they say that their present work aims to establish a benchmark to see what contraction shapes are best and what cross-sectional shapes are good. They say that an axisymmetric cross-section with a circular cross-sectional shape is believed to be optimal for achieving a uniform flow. However, that's not strictly true actually, because in the corners you do get worse flow, but it's also very hard to manufacture, which means that the cost goes up. Then they say that Meta has mentioned that the corner flow for a well-designed contraction is localized and does not affect the flow quality over most of the span of the test section. That seems a little bit dubious to me, like saying that the flow in the corners don't affect your wind tunnel is kind of like, it seems like a researcher who doesn't really want to fix this problem, so they just say, oh yeah, it's not important. I would consider that it is important because it does affect the pressure and the boundary layer build up and etc. So we'll see if that's the case or not. And then they say that in fluid mechanics, they look at cross sections, circular, square, and octagonal, which we mentioned earlier, and rectangular, which is kind of like circular, kind of like square. Sorry. Then they said that they looked at the circular, square, and octagonal, and the hydraulic diameters were the inlet was 1.1 meters and the exit was 3.5. This gave a contraction ratio of almost 10, so it's quite high. This means that you're going to have a very good flow quality. And with the contraction shape, so the path that the contraction will follow, they have 4 different contraction paths. 3 are third order polynomials, and 1 is fifth order polynomial. We mentioned earlier how some researchers wanted to raise to the 5th power instead of just third, so they want to look at that. And they have a graph here in figure 1 for those of you playing at home, and it shows these curves. So for the first contraction, which is 5th order, it's pretty nice. It's fairly gentle. The second order, which is third polynomial, is probably the worst. Like I can just see right here that it's not very gentle. It's got a much steeper gradient, and then it has a couple of inflection points. They're not good. Third and fourth contractions are even better. Like they're really the best. They're very nice and gentle. Number 4 looks really nice, and you can actually get a good idea as to how good a contraction will perform just based on this slope here. If it's very gentle, it's usually going to perform much better. You don't want it to be sharp. You want it to be a gradual incline and not have too many inflection points. So the more smooth and gentle, the better. And then they looked at their contraction. They said they're going to look them at 6 meters per second and 16 meters per second, because you can have different boundary layer formations, different flow separation formations in the contractions. They want to look at both of these. And interestingly, they say here, according to Batchelor, a contraction ratio of 9.88, which is what they have, can reduce the axial velocity fluctuation by a factor of 0.24. Therefore, the turbulence intensity of the axial velocity at the contraction exit will be about 40 times smaller than that of the contraction entrance. That's a lot. I mean, if you think about it, if your wind tunnel has a turbulence intensity of 0.5%, then that means at the start of the contraction, it's 20%. So if your velocity there is 5 meters per second, it can range between 4 and 6 meters per second. And that, when you think about it, actually makes sense, because with the wind tunnel, what you have is your fan upstream, then your honeycomb, then your mesh. Now the fan does not uniformly accelerate the flow, depending on the type of fan you have. So if you have just an off-the-shelf blade, the flow, as you go further out from the center of the fan, the flow is going to be faster because the blade is moving faster and it's doing more work on the flow. Now, if you have blades that are designed well, it means that they won't, because you'll take into account that increase in velocity as you go further out, the radial velocity, or the tangential velocity, sorry. But in the middle of the fan, regardless of what blade you have, the middle of the fan is going to be the center rod, and there isn't going to be any flow acceleration at this point because there are no blades. So you're going to have this dead spot in the middle. So that does make sense in terms of having a turbulence density of 40 times more. You have this fan which doesn't accelerate the flow uniformly. That could make sense. Now let's move on to their results. So they look at the effect of the contraction wall shape. So remember how we said that there are 4 different slopes, and they range from being pretty shoddy to really nice and smooth. And they say in all four investigators' contractions deliver barely distinguishable velocity contours. The pressure loss of a contraction might be a concern about the long-term operating costs. So they have, first of all, this figure which figure 5, for those of you playing at home, it shows the axial velocity and the static pressure contours with the first case. So this was the worst slope in my opinion. And it shows that, as you'd expect, as you go further through the contraction, the axial velocity increases dramatically and static pressure drops. This means that you have a pressure drop. And the pressure drop means that the fan has to work harder to push the flow through, which means you have to use more energy, which isn't a huge deal considering that the fan is using a lot of energy to begin with, but over time it can stack up. And they reported the pressure drops along the contraction at 60 meters per second exit. And what they found was that it's around 60 to 80 Pascal drops. That's not too bad, but it is something. Now, interestingly, one cool thing they have here is they break down the different components of the wind tunnel and the pressure drops along them. So they have the honeycomb, and they show that the pressure drop is only 12 pascals compared to 5 screen meshes, which is 160 Pascal drop, and that's huge. Now, that's not unexpected. If you listen to podcast number 32, which is about turbulence densities, we go through how mesh screens affect the pressure drop, and this is in line with what you'd expect. It's quite a big drop. It does depend on how open these screens are, then that also affects the flow quality. So this is really, there's a massive knock-on effect. The contraction, that makes up for about 1/6 of the pressure drop in this wind tunnel. So that's quite a lot. And that's why you want to optimize it. Now, they say that the velocity profiles at the contraction exits are shown in figure 6. And let's look at that. They look very similar, but the contraction number 4, which I mentioned earlier, I thought looked the best. They have the smallest boundary layer, and that makes sense. They also have the axial velocity standard deviation of contraction 2, which was third order polynomial, which was okay. It's higher than the other 3 contractions. The other 3 contractions were very similar. And they say that this might result because the higher first, second order derivatives of the slope. So let's talk about that. What they have are the first and second order derivatives of these 4 slopes. And what this means is it shows you how rapidly the slope changes, how rapidly this surface changes. When you have a very high, like a very non-uniform first derivative. So for example, in here you have a peak on one of them. That means that the geometry is changing quite a lot and there's an inflection point. The second derivative is even worse. So you have some discontinuities and they are disconnected by a long way. This means that the contraction is quite angular in terms of relatively speaking. And that's not what you want. You want them to be very smooth. I mentioned earlier, contractions 3 and 4 are much better. They're much smoother in both the first and second derivatives. So that's how you know that they're better. So we conclude from here that the first and third and fourth derivatives are quite good. The first, third, and fourth contractions are quite good. Number 4 being the best, and number 3 being quite good too, which is what I mentioned earlier, considering that the third and fourth contraction slopes or geometries were much smoother, which is what you want. So now they talk about the contraction cross-sectional shape. Actually, I forgot to mention, this finding also indicates that the 5th order polynomial was not the best. The 3rd order was actually better. So when Meder and Bell raised to the 5th, that wasn't necessarily the best case scenario, and the 3rd would actually win out in the end. So that's a bit of an upset there. So let's move on and talk about the contraction cross-sectional shape now. We've gone through the geometry. Let's go through the cross-sectional shape. They say for the same contraction wall shape, the differences in pressure loss among the 3 different cross-sectional shapes are less than 10 pascals. So what that means is they perform quite similarly in terms of the pressure drop. That's okay. And they say that the wall shape is a more dominant factor for the pressure loss along contraction than the cross-sectional shape regarding the pressure loss. So what that means is the path that the contraction follows, so that whether it's 3rd order or 5th order, that affects the pressure loss far more than the cross-sectional shape, by a long way actually, by about double actually. Now, they say that the case with an octagonal cross-sectional shape shows a better performance in terms of fluid mechanics with a thinner boundary layer. So let's look at that quickly. They have a figure 11 here, and they plot the cross-section of a square versus a octagonal cross-section. and they look at the velocity in this cross-section. If you look at the corners, the boundary layer in the square one in the corners are okay, it's not bad, but it's not as good as the octagonal shape. And both of these I suspect are going to be much better than the circular one once you hit the test section, because the test section now you have those corners. So the octagonal one performs very well in terms of the boundary layer. There's very little dead regions, and the boundary layer is much thinner, so that's good. They also say that the octagonal cross section performed better when it came to the pressure loss. It's lower, so that's even better again. And they also say that their experience shows that the octagonal one has a lower difficulty for manufacturing and a lower cost, which is better again. So before we move on, I just want to say, make sure you check out what we do at Aerodynamics, check out the instrumentation we do. So we do the atmosphere hawk, which actually measures the temperature, barometric pressure, and humidity in your wind tunnel, which is what you need when you want to accurately measure the density or calculate density. The reason why you need to have an accurate density is because the density affects pretty much everything you do. I mean, it affects the velocity of your wind tunnel, it affects your non-dimensional coefficients, such as the lift and drag coefficient that you will calculate. It will affect the CFD that you have when you want to validate it. You want to have the right density in your CFD to match your wind tunnels. So you need to have the density correct. This instrument does that for you, and it's really good. It's very easy to use, and it just does it accurately. Also check out our PRV and traverse system. We also have a new FlowViz method called the Rayleigh scattering FlowViz method. We're getting that up online as well, so check that out as well. Check out our courses. We do theory like this. We also do experiments, and we also do CFD to make you a better aerodynamicist. We also do the International Aerodynamics Conference, which is a conference every year. So check that out. So let's get back to this paper. So in conclusion, they said that, I'll read the conclusion because they break it down into 4 nice parts. They say the different contraction wall shape investigated in the study result in the pressure loss difference up to 17 pascals, contributing to about 4% in the pressure loss of the entire wind tunnel system. So what they're saying is, depending on the contraction slope that they employ, this pressure loss difference could be up to 20 pascals almost, which is a 4% change in the pressure loss in the entire wind tunnel. Now, compared to the cross-sectional shape, there's only about a 10 pascal drop, or 10 pascal difference. So that means that the cross-sectional shape doesn't really affect the pressure loss nearly as much as the contraction slope. They also say that the first and second derivatives of the different contraction wall shape equations can provide a hint for the quality comparing the flow characteristics at the contraction exits. So what this means is when you have much better behaved first and second derivatives, so they're much smoother and continuous, the quality of the flow is usually better. And that's to be expected, because if you have smoother first and second derivatives, it means that there are fewer inflection points, and that's what you want. They also say that the octagonal cross-sectional shape of a wind tunnel shows a better fluid mechanics performance in terms of the thinner boundary layer, a lower axial velocity standard deviation within the core, and a lower pressure drop. So that's again what we kind of expected that, because the octagonal one is halfway between the circular and halfway between the square, and so it's kind of the best of both worlds. It's a good compromise, and they're much easier to manufacture as well. I mean, even the square one, I've had to install a few square contractions, and they're much harder than you'd expect, because not only are they moving in terms of one dimension, but then there also is on the sides, they get smaller. So you have to make sure you align them properly. Otherwise, if you don't align them properly, you lay, for example, the floor, you lay the side one, and they don't match up properly. So you need to jiggle them around, and they're much harder than you expect. Octagonal is much easier because you don't have to get as much of the surface area right in one go. You only have a smaller surface area to worry about. So they are easier to install as well. I can tell you that. So finally, they say from an engineering application, a wind tunnel contraction with an octagonal cross-sectional shape not only has better performance in terms of the flow than the circular or square, but it's also lower in terms of lower difficulty in terms of manufacturing and cost. And compared to the cross-sectional circular shape, the octagonal cross-sectional shape has a larger cross-sectional area, which results in a smaller blockage ratio. So let's quickly touch on this. Podcast number 39, we're going to blockage ratio. So if you want to get more about that, listen to that. But just quickly here, the blockage ratio is very important because it affects how accurately your flow is being replicated in a wind tunnel compared to real life conditions. If you have a bigger blockage ratio, it means that the flow has to accelerate more around your body to get through, and that changes the flow physics and changes the drag and lift of this object and all the other characteristics as well. So the octagonal cross-sectional shape increases the cross-sectional area, which reduces the blockage ratio, and that's what you want. Okay, so that's the end of this podcast. Make sure to like and subscribe. Check out what we do here at Aerodynamics. Check out the instrumentation we do. Check out the courses we do. Check out the consulting we do. If you've got a problem, we can solve it. And check out the courses we do. The conference we put on every year. Links in the description. Peace out, amigos.